So let's continue. Question 6. We have the vector equation of a line. We have the equation of a plane P, and part 1 wants us to show that the line lies on or lies in the particular plane P. Now, visualization is very important with such questions. So I've drawn, I've tried to draw this out here. So if you have a line intersecting your plane at a particular point, and hopefully with the side view below the original diagram, it'll be easier to understand. So it's just intersecting it at a particular point, like at a particular point uh, of lambda, one could say, because lambda is basically how much you multiply your direction vector with, right? So there'll just be one particular point of intersection with the plane. On the right, however, where it lies on the plane or lies in the plane, this is where it lies on or in the plane at all points. So all points on the line, which would be infinitely many, would lie on the plane, would satisfy the equation of the plane. You wouldn't have just a particular point. And if it's not intersecting, hopefully it's easier to see this with the side view as well. The idea here is for any value of lambda for any particular point on the line, it's not going to satisfy the equation of the plane, because there are literally 0 points of intersections, and this should come in hand as we go about this question. So first, let's just write out the vector equation of the line. So it says that this is line R. It passes through point 1, 2, -3. Just reading it off the question at the moment. Lambda into its direction vector, which is this, right? We can simplify. Well, we can simplify R into just one bracket. So it's 1 plus 2 lambda, 2 minus lambda, minus 3 plus lambda. Yeah, so this is also equals to R, right? And what is basically R, right? R basically gives you a particular point on the line. It's talking about a particular point, a particular set of coordinates on the line, one could say. So particular value of x, y, and z, which basically is a particular point on the line, right? Now, in the equation of the plane, you already have the equation in terms of x, y, and z. And from the equation of the line, we already have expressions for x, y, and z. And if it lies on the right at the moment, we're trying to calculate the point of intersection, and because it lies in the plane, we have to show that there would be infinitely many points of intersections. But to do that, to show that, we have to calculate or go through the method for showing the point of intersection, which is where your x, y, and z values for the equation for the equation of the line, you input them into the xyz values of the equation of the plane, because in points of intersections the xyz value should be the same, right? It's a constant or the same point in the plane and on the line. You just pop this in. So you have, what was this? It was 3x. So that'll be 3 1 plus 2 lambda, because that was the expression of x that we got from the line, plus 2 minus lambda, that is y, minus 5 3 plus lambda, that is z, 20. And then you try to simplify it to look for a value of lambda. So I just skipped past the algebra here, but it's important to understand the significance of the answer we're getting and how this shows that the point lies on the plane. What does this mean? It's saying that 20 is equals to 20, right? And what's happened here is that your lambda has been cancelled out. Like it's as you saw here, 6 lambda minus 6 lambda, so that is cancelled out. What does this mean? This means for all values of lambda, basically for all particular points, because as you notice, the only lambda was really the only thing that we were varying to figure out different particular points on the line. So like let's say this point would have a value of lambda 1, this point would have a value of lambda 3 upon 2, for example. This particular point might have a value of lambda I don't know, 1.2, and so on. But what we're saying here, lambda is not even in the final expression. So here for all values of lambda, 20 will be equals to 20, which is like this, that the equation of the r values of the line will satisfy the equation of the plane for all particular values of lambda, which basically means for all points, because for all particular values of lambda, the line lies on the plane. And if you link it back to here, here the idea is like for all particular points of lambda, the line lies on the plane. Over here, it'll be more something more of like, let's say lambda 20 is equals to 20. So here the point of intersection will be where lambda is equals to 1, because this is intersecting at a particular point, right? If you have your non-intersecting lines, then the result should somewhat be like similar to this, for example, that 7 obviously isn't equals to 20. And since this is not in terms of lambda, for all points of lambda, whatever point of lambda you put, it won't matter. It still would never be equals to 20. It will still never satisfy the equation of the plane, and hence will never lie on the line. Hence the line will never lie on the plane. That's the idea. Whoops. So hopefully it's clear now. We proceed. A second plane is parallel to L, okay, so, and perpendicular to P, and contains the point with position vector, okay, so this is the point on the plane, and you have to find the equation of the plane. So let's try to picture this. Let's try to draw it out. So you had, what do you say? You had P. I'm drawing this, just drawing the side view. This is, let's say, plane P. And here this guy is saying that the second plane, let's just call the second plane, I don't know, let's just call it A. So the second plane A is perpendicular to P. That's what we know. We also know, well, in fact, let's just finish this train of thought. So if it is perpendicular to P, if you think about it, what was the normal vector of P, right? Because we can figure out the normal vector of P from the above, because we have the equation of P. And I'll look at that in just a sec. But the idea here would be that since the normal vector of P is also perpendicular to P, and the plane A is perpendicular to P, one can say that the normal vector would lie on plane A, or at least the normal vector would be parallel to plane A, as we're calling it. So the normal vector is parallel to plane A. Another thing we know is parallel. The second L is parallel. So the direction vector, because the direction vector is going to help us actually figure out stuff. The point is just something to help you get on the plane, on the line, right? So the direction vector of line L is also parallel to plane A. So what do we have here? If we have, let's say, if this is plane A, then in a manner of speaking, because these are just directions again, like you could say your normal vector is somewhat like this. Maybe your direction vector is somewhat like this. I don't exactly know. The idea here is that they're both parallel to the plane. And understand what I'm trying to figure out here. I have a point on the plane. What else do I need? The equation of the plane is R scalar product n A dot n, where A is basically a point on the plane. We already have A. The only other thing we need is the normal vector of the particular plane, of the new plane, right? And how can we get that through here? Since we know that there are two vectors parallel to the plane, if we take the cross product of that particular vector, we should get, let's call this n2, which is the normal vector of the plane. And that's basically something that we're going to calculate. That's why they've given us 5 marks. Okay, so what is the, let's just write down the normal vector of the original plane. You can just read it off here. So basically the coefficients of the equation, so that will be 3, 1, and minus 5. And that is 3, 1, minus 5. And what is the direction vector of the line that we have here? It was given above. What was it? It was 2. So read it off here. So it was 2 minus 1 and what was it? Sorry, 2 minus 1 and 1. You have 2 minus 1 and 1. There are a couple of ways to go through with the cross product. I'll just show you the way that I find is just the easiest to remember. So will be a bit of a Jugaru way. So we need to basically find the cross product of these two vectors. Again, this is like if it's one vector here, one vector like this. The third vector would be the one that would form a 90-degree angle with both vectors. It's a bit difficult to visualize, but imagine if these two vectors are on the same plane, then the third vector would be the one coming out of the plane, because only then would it form a 90-degree angle with both of these vectors. How do we go about? Well, the Jugaru type method is as follows. You have I, you have J, you have K. You just have to remember this a bit. It's plus, minus, plus. So your J would always be minus. So write it out. You have 3, 1, minus 5. You have 2, minus 1, 1. Right? Now, the way to look at this, or the way I do this at least, is if I want to figure out my value of I. So I look at the other two values. To calculate I, so if I'm trying to figure out if this is I, J, K, and I'm trying to figure out what these values are. Sorry. So I'll be looking at the two sets of values apart from I in order to calculate I, and I'll find the determinant of that, somewhat similar to your matrices type thing. So for I then, I would have 1 into 1 minus 5 into minus 1, which should give me a 1 plus 5, so that should be minus 4. So your I value is minus 4. Then you do this again for J, and for J you're going to be looking at these two now, the two values apart from J. But remember, this is minus J. Like, that's just something I'm afraid you'll have to remember. So that will be 3:1 minus 5 into 2. Right, that gives you 3, 10 plus 13, should be 13. But don't remember the minus sign here, so this is minus J. So you want to write for J, that'll be minus 13. Let me just rub this. Yeah, so for K, as we did for the previous two values, you just look at the other two, right? So K should be minus 3 minus 2, should be minus 5. Gives you minus 5. So what is this? This is your normal vector. The vector normal to the plane, to your new plane, as we figured out here, right? Now what do? Your equation of the plane is r dot n into a dot n. R is x, y, and z, so a particular point or line on the plane. Dot n is minus 4, minus 13, minus 5. Lots of minuses here. Anyhow. And you equals this to a is the point. We have been given the point that is from here 3, minus 1 and 2. So that's 3, minus 1 and 2 dot, again the normal, which is minus 4, minus 13, minus 5. And now you just algebraically solve. You basically do your cross product and solve to get the value. So that's the simple part. There you go. Okay, so question 7, I believe. Yeah, differential equations. Nice. Okay, so a water tank has vertical sides and a horizontal rectangular base as shown on the diagram. The area of the base is 2 meters. Okay, so the area is 2 meters square. At time t is equal to 0, the tank is empty. So we know where t is equals to 0, the volume of water in the tank would be 0 because the tank is empty. In fact, I don't think they look at volume here. Okay, they're looking at height here. So a better way to put it would be, when time is 0, the height of the water column in the tank would be 0 because the tank is empty, right? And the water begins to flow into it at a rate of 1 meter cube per hour. Okay, that's your inflow. At the same time, water begins to flow out from the base at a rate of 0.2 root h meter cube per hour. So what can we write as rate? Rate is the change in volume, right? It's the, so dv over dt is basically your change in your rate of change of volume, right? So that's something we can write. And how is the volume changing? It is increasing by 1 meter cube per hour. However, it is decreasing by 0.2 root h meter cube per hour. So this gives you your expression for dv over dt, where h is the depth of water in the tank after time t hours. Form a differential equation satisfied by h and t and show that the time t hours taken for the depth of water to reach 4 meter is given by, okay. So if you look at it carefully, you'll note that they want this in terms of, well, time, and they want this in terms of h, so not in terms of volume, basically. Can we figure out an expression for volume? Because I can anticipate that we're going to have to use chain rule here. So volume was the base area, like the volume for obviously a particular shape of this type would be your base area into height. When the base area is fixed, right? The base area won't change. Base area, been given the rectangular base is 2. So volume is 2h. And I'm going to differentiate this now for reasons that will become more clear as we form our well, as we apply the chain rule, right? So we have dv upon dh, we have dv upon dt, we don't have dh upon and like dh, the rate of change of h is unknown to us, but it might be helpful to find that. Okay, so we go about, if you want to form a chain rule from this, so we have dv here, we have dv, yeah, okay, so that would be dv upon dt should be equals to dv upon dh into dh upon dt. And the way to know that you formed your correct chain rule or equation is to see if you cancel out, because these two can cancel out, will your right hand side value be equal to your left hand side value, and that is true in this case. So you formed a correct equation. Anyhow, we had dv upon dt. Kya tha wo? That was plus 1 minus 0.2 root h is 1 minus 0.2 root h. Dv upon dh is a constant of 2 into dh upon dx, we don't know. So let me just take that as x for now, right? Now, how should we proceed? At time t is equals to 0, the tank is empty, and the water begins to flow out at a rate of sahi. So if we just calculate x again, remember, is dh upon dt, so that will be 1 upon 2 minus 0.2 upon 0.2 divided by 2, which is like 0.1 root h, right? What is this again? This is dh upon dt. In fact, I think a better way would just be to keep this as let's not break it up into fractions yet. Okay, so 2 was going and dividing there, so it's 1 minus 0.2 root h upon 2, right? And now the key here is to think you want your expression in terms of h, and you want t and dh, right? So what they've basically done here, they've in fact gone ahead with the differential equation. So you take all your values of h to one side and all your values of t to the other side. So dh remains here, and 2, well, 2 goes on that side because you want to isolate t on one side to get just t, right? So that's 2 upon 1 minus 0.2 root h is equals to dt, or rather I can write 1 into dt. Now if I integrate on both sides, what will happen here? If you're integrating with respect to t and it's just 1, it'll just become t. What will happen here? Well, they don't want us to do the integration in this particular part. What they do want us to do is to simplify it a bit. So how can I do so? I can simplify by writing 2 upon 1 minus, again, remember what is 0.2? 0.2 is really 1 upon 5 root h dh. So t is equals to, if I simplify 5 in the denominator, I'll take 5 as LCM. That will flip to the top. That's 10 upon 1 minus root h dh, right? And the limits they've given you as to 0 to 4. And what's the logic behind that? What you have to in fact show this is because you want to figure out the time in t hours taken for the depth of water to reach 4 meters, because this is in terms of h is initially 0, and now h is going to be 4. So you want to figure out the time it takes for it to reach 4 meters, and there you go. You've shown this through my very bad handwriting, but you've done it using, okay, use substitution. Nice. Find the value of t. Okay, so understand what you need to do in use substitution. You need to do 3 things. You need to obviously substitute in terms of your u. So you need to substitute in terms of your u with the expression that you're given in the integral. You also need to find a particular expression for dx in terms of du, because you would need to substitute that as well. And you need to like fix limits as well. So your limits then need to be in terms of u, not in terms of x. So the first thing I always do, I find an expression. I do the second part first. So you just find an expression of dx in terms of du. How do you do that? Well, in this case, it's not dx. In this case, it's dh rather. That's the variable we have. So the above expression is in terms of dh rather than dx. So to do so, to find an expression in terms of dh in terms of du, I differentiate this particular expression. So that should be du differentiating u in terms of h. So du over dh, which should give me minus 1 upon root h, I believe. Have I differentiated correctly? This will be power half. As it gets minus half, the die goes down. 1 upon 2, I believe. So yeah, because that's minus h raised to the power half. That becomes half shift. So that's 1 upon 2 minus half. Yeah, so that's fine. And now you want to make the h the subject here, which is basically minus 2 root h du. So you've done one bit at least. Now you want to put it back into the original equation that you have. So you have an integral sign. You have 10 upon 1 minus root h. Do you have 1 minus root h? Oh, I'm sorry, a mistake we made before. Because here when you're taking your LCM, this would in fact become 5. Sorry, an algebraic slip by my end. So yeah, you have 5 minus h. So basically here, this is 10 remains as it is. And in the denominator, you have 5 minus root h, which is exactly your substitution. So you can substitute that with u. And dh, instead of writing dh, you can write the expression for dh that we calculated here, which is minus 2 root h du. But the issue here then becomes that we don't want anything in terms of root h. So we want to further substitute root h with the value of u. And what is that? If u is 5 minus root h, then root h should be 5 minus u. And we take this, we substitute it here, because again we want this value, this expression of the integral to be completely in terms of u, not any other value. So this is going to be minus 2 into, well, into 5 minus u du, right? And if you simplify, you get minus 20, so minus 100, I believe. Minus 2 is 10, yeah, minus 100 plus 20 u upon u du, right? So what we've done here, we've done our second step, we've done our first step. We're still left with this though, fixing limits. So what were our original limits in terms of h? We had 0 and we had 4. We need to find out the equivalence of u. So just put it into the substitution equation that's given to you. So when h is 0, u is 5 minus 0, which means u is 5 when h is 0, making this 5. When h is 4, u is 5 minus root 4. 5 minus, what is root 4? Root 4 is 2. 5 minus 2 is 3. And this is 3. This makes this a little problematic. Why? Because you want it to be going from your lower limit to your upper limit. Here it's going from 5 to 3, where 5 is a larger value than 3. So it's going, so in fact, here it's going from your upper limit to your lower limit. You can fix this, however. How do you fix this? You just simply switch your limits and add a negative sign here. And whatever you have inside remains the same. You can take your negative sign inside just to simplify, which gives you 100 minus 20u upon u, right, du. Now it'll be simpler. Do we have to integrate? Yes, we do. And I've been very wasteful with my space here, but it's fine. And I mean, I have bad handwriting. Maybe if I write too small, then it's really difficult to figure out anything that I'm writing. Okay, so it's just much simpler here to just break this. So that will be 100 upon u, which I can just write as u minus 1, because that's just easier. Okay, wait, but u minus 1. Remember, we can't integrate minus 1, so that's not going to help. Okay. So you can write it as this minus 20. You have 3, 5, 20u upon u. You can write this as okay, so let me just fix this. And this is cutting. So you just, if you split it apart, it makes life much easier for you. Here is just easier to take your 100 on the outside. And because the idea here, if you have u power minus 1 or 1 upon u, what you're going to use is this particular property. So the integral of the function of something in the denominator and its differential in the numerator is ln of the denominator. So here that matches because u is in the denominator. The differential of u is 1. That's in the numerator. So here we can simply write 100 ln u minus 20 integral is simply going to be 20u. You just have to add your appropriate limits. Let me continue this on the separate slide because I've been very wasteful with my space here. So we've integrated, and now we just have to put in our limits, which is pretty, like menial work, but let's just go ahead with it. 100 ln 5 minus 25 subtracted by our lower limit, so that's minus 100 ln ln 3 minus 23, right? And you simplify. An easier way to go through this is just to take ln 5 power 100 minus, this will be 100 as well, minus ln 3 power 100 minus, what would this be, 60? Okay, in fact this will be plus, because if you multiply the minus sign inside, it'll be plus. Okay, so if the two ln's are subtracting, you can just condense it into one, where 5 upon 100 would be dividing by 3 upon 100, which is kind of like the same thing as writing 5 upon 3 into 100, which is also like the same thing of writing ln 5 upon 3 and take 100 as the multiple. So I took it as the power just to condense it. Now I took it back in the multiple because that just makes my life easier. Minus 40. This should be your answer. Do they want it in exact? Do they want you to find a numeric value of it? You just need to find the value of t. So you'll just pop this into your calculator. Let me do that. So I'm getting 11.08, but because this is my final answer, I will round this off to 3 significant figures. So 11.1, t was in terms of Rs. If you want to write your units, doesn't really matter. But so take 11.1 Rs for the tank to fill up to 4 meters. That's a pretty slow pump or whatever. Anyhow, we have complex. Throughout this question, the use of a calculator is not permitted because but what you can do, you can use your calculator to check whether you've come to the right answer. So you have the polynomial pz, and you have the complex denoted by u. Showing all your working, verify that u is a root of the equation pz, right? Okay, so if u is a root of the equation, right? If u is, it's minus 1 plus I, and if this is the root of the equation, then pu should be equal to 0. Well, if I put u in, if I put instead of putting the variable z, if I put in u everywhere in this particular expression, it should give me 0. Only then would it be a root of the equation. So you just put it in, minus 1 plus I raised to power 4 plus 3 minus 1 plus I raised to power 2 plus 6 minus 1 plus I plus 10, and you have to show that this is equals to 0. Minus 1 plus I might be a little difficult to expand without our calculator, so I'll just subdivide this into minus 1 plus I square into minus 1 plus I square. You can do the rest though, so this will be 1 what do you call it, minus 2I plus I square will be here. You can just write this as minus 1 plus minus 6 plus 6I plus 10 is equal to 0. So it's just algebra from this point on. So let me just skip through that. So here are the steps in case someone wants to go through them. I've used the green color to cut, where like if it was 1 and minus 1, I just cut that. If it was minus 6I and plus 6I, I just cut that because that would be equal to 0 anyways. But you verify that. And you have to find the other 3 roots of the equation pz is equals to 0, and they're giving you, this is for 7 marks, so won't be easy. Okay, so just sit back. This will take a bit. Now this is the polynomial, okay, z power 4. Okay, so understand, in such cases complex roots always come in conjugate pairs, which means is, let's say u was a root, u star, which is its conjugate, should also be a root. So u we know is a root, which is -1 plus I. With its conjugate, you just flip the sign of the imaginary part of it. That is -1 minus I. So we've already figured out one of the roots. So you have two roots, that's for sure, right? And we can write this. We know that u is, well, -1 plus I. Like, if you remember, if x was 2 and you roll this in terms of a factor, x minus 2 ho jata hai. So that's kind of like the same thing. So u plus 1 minus I and u plus 1 plus I. These are two of your factors. What are the other two factors? The other two factors are going to be something, right? So in fact, here, let's not write it with u, let's write it with z, because that's the expression that we have. This is z, this is z. The other two factors are going to be z, let's say, the other two factors are x plus yi and its conjugate, which is x minus yi. If you want to write this in terms of a factor, if z can be this, we have to take this on the other side. So x minus yi can be 1, and z minus x plus yi can be 1. And this should be equals to the polynomial. So we can use comparing to help us here. So one way of doing so would just be to multiply all of these 4 brackets. You would get your something in terms of z power 4, which is what your polynomial is given to, and you just use comparing. However, that may become a little tedious. So what alternatively we can do is we can just multiply these guys, the two factors that we know. So we can multiply these two to get an expression in terms of z square, and then we can use some division. So this should become z square. Okay, I'm just going to multiply these two brackets. It's just going to be very simple algebra. So skipping past that, and you're getting z square plus 2z plus 2. Now to calculate, well, z square plus 2z plus 2 is obviously going to be multiplying by something to give your final polynomial of z, which is in terms of z power 4. To find that something here, you can just simply use long division. So what is pz? What was the polynomial? Z power 4 plus 3z square plus 6z plus 10. So it was z power 4 plus 3z square plus 6z plus 10. So 3z square plus 6z plus 10. And you want to do its long division. Long division with what? With z square plus 2z plus 2. Okay, so z square, if we multiply z square by another z square, or let me just use a different color for this, in fact, just to keep things distinct. If you multiply by another z square, we get z power 4 plus 2z square plus 2z cube, rather, because if you multiply 2z plus with 2z square, you get 2z cube plus 2z square, right? And you're just gonna flip the signs here, because remember, this is overall, this is multiplying, so a plus would become a minus here. So z power 4 minus z power 4 is 0, which is what you exactly wanted, which is why I multiplied it by z square. 3, well, okay, something to take note of, to be a little careful of in this. is do write it out properly even if you don't have a particular power. So this is actually plus 0z cube, then it's plus whatever you had, I keep forgetting, 3z square plus 6z plus 10 plus 3z square plus 6z plus 10. It just makes life easier. Okay, so what do we have here? We were using blue. Okay, so 0 minus 2 is minus 2z cube. 3z square minus, I know it says plus here, but since you're subtracting overall, it would become a minus. So 3 minus 2 is plus 1z square, right? And what would happen is your next value comes down and joins them in the party. Okay, now you have to somehow multiply this by something that equates it to minus 2z cube, and that would be minus 2z, right? Because then you're subtracting overall, remember. Minus 2z into z square is minus 2z cube. This would be minus 4z square minus 4z. And again, remember to flip your signs here because you're subtracting. So it's actually minus 2z cube plus 2z square, 2z cube here, which gives you 0. This is what you want. Plus and plus, this is 5z square, plus and again plus, this is plus 10z. And this comes here as 10. This joins the party. Now, how do you equate this? You just multiply by 5, I believe. So that gives you, you're subtracting overall, that gives you 5z square plus 10. What's wrong with my stylus? Plus 10z plus 10. And they should all be equals to 0. So, which is a good sign because it shows that that this and this are basically expressions of factors. Anyhow, so you've already figured out, you already know the roots from this, so that's good. You don't from this. So you take this particular quotient, I believe you call it, and you're going to then try to figure out the roots from here. And for that, this has to be equal to 0. So understand what this basically looks like. It looks like z square plus 2z plus 2 multiplied by z square minus 2z plus 5 is equal to 0. That was basically, or is equals to the polynomial rather, right? And for the polynomial to, and you equate you make the polynomial 0 to get the roots. So you can just equate this with 0. Okay, so simple middle term breaking from this point on. So in fact, the middle term breaking wasn't working. Obviously, it was. So I just used our quadratic formula. And just one thing I want to point out here: you have it in terms of negative root, which obviously you can't do through just real numbers. You'll have to use a complex number here. How do you do that? What you can do that you can do this is do minus 1 root into root 16 is the same thing as saying minus root minus 16, right? Now what you do, 2 plus minus, root of minus 1 is by definition I, root of 16 is 4 upon 2, which basically gives you 1 plus minus 2i, which are your other two roots. So you had two roots in the beginning. Let's write them down as well. What were they? If I believe I've written them here. So minus 1 plus I minus 1 minus I. So you have minus 1 plus minus I. So these are your 4 quadratic roots that they wanted. And